Okay, sorry about that. So, okay, I was saying bars means mature disk, basically. It's just a disk that is dynamically cold. And there has been quite a bit of interest along the years to look at the presence of bars, looking back in redshift. So basically, as I said, you expect this to be more turbulent at higher redshift when they have actually just formed or along the way, basically. So they're thicker, more dynamically hot. There's more dispersion in these disks. They're more puffy. And the idea has been to actually look at the bar fraction. Oops. The bar fraction as a function of redshift. This I'm referring to some paper that at this time, it was basically a paper that didn't really put a final dot to the conclusion as to when galaxies start forming bars, but at least it gave a whole lot, there was a lot of discussion that came to a pause with this paper. So just basically summarizing it for you, we have that today, 65% of all spirals have bars. This is including strongly barred galaxies, where you can actually see a thin, very well-defined bar, and intermediately barred galaxies, where the bar is weaker, a little bit broader. It's not as easy to detect. And it presents not such a strong break to the axisymmetry of the disk. And when you go out to higher redshift, and this is using HST data, ACS, so this was really a nice resolution at the time. I mean, it still is incredible resolution. And this was up to redshift of 0.8, which corresponds to when the universe was 6 giga-years old. So this work has actually been pushed forward and then has continued on, especially with a new work. This paper from Zoe Leconte just came to the archive. It was submitted. I mean, it'll probably soon be accepted. But this is actually looking at the bar fraction extending out to higher redshift, because with JWST, we're actually starting to see bars at much higher redshift. So these are a few. This was paper from Guo, and this paper just came out on Nature a couple of weeks ago with here pretty clear bars. So having disks with such nicely formed and detectable bars is actually a surprise, considering what we knew before. 15% of all spirals had bars at 0.8, so we were expecting, I mean, it continues to show a drop, but there starts to be a little bit of contention, especially when simulations actually show the expectation of there to be a lot of bars. So there's a lot of interesting stuff being discussed around this. So another interest in looking at the bar fraction here, and this plot, this is from the same paper based on ACS data, was to actually look at the bar fraction as a function of the galaxy mass for different redshifts. So you have these 3 different curves. This is for the highest redshift that was probed at the time, intermediate redshifts, and low redshift. And what we see is that the bar fraction, it declines towards a higher universe, a higher redshift. You can see the curves actually just going down. But this is almost exclusively in the lower masses. And note that by lower masses, we are still looking here at masses greater than 10 to the 10. And actually, when you look at the higher end, the bars formed, they seem to be quite established. So basically, independently of the redshift that you look at within the error bars, you see that the high mass end already had its bar fraction established. So really, all the bar formation action, basically, which remember, we're connecting this. It's not only the beauty of finding bars, but it's actually the beauty of being able to connect this to the coolness of these disks, to the maturity of this disk, to the dynamically coolness of these disks. So the bars, I mean, the internal, just going back to what we were saying, I mean, galaxy shapes are associated to past events. They tell us something about the disk maturity, but also the internal, I mean, I skipped this part. We can talk about it at some other point. But the internal galaxy evolution can lead to changes in the internal structure. And just the case of the bars, but also spiral arms, they trigger quite a bit of gas motion within galaxies that can have a huge impact to host galaxies. In the case of bars, for instance, here, there's this beautiful bar from NGC 1097. It has been proposed. I mean, it was shown in 2004 with a a few, just tens of galaxies, but this is something that we're still looking at. It would appear to wash out the metallicity gradient. So basically you have the bar that is moving gas and stars around, so you will naturally be washing out, moving around metals too. So reorganizing the metallicity gradient, in quotes, a natural, that would be a natural pointer to how the galaxy was formed. So having a bar would actually wash this out. It leads to a central accumulation of gas that leads to nuclear starburst, to the formation of, to the growth of bulges, and to the change of these bulges that could be more classical bulges, very spheroidal, to bulges that are acquiring disk properties and are called the pseudobulges with more rotation. And potentially too, there has always been an interest of connecting them to the feeding of an internal AGN with a set, for instance, of a primary bar and nuclear bars, secondary bars, connecting them through towards the center. So basically, the bars in this case, they do have a very big impact in changing the internal structure and leading to internal changes. So the shapes of galaxies, I hope I have convinced you up to now that they do give us insights to the galaxy formation history, to how the mass was assembled. And we're interested very much also in looking at what masses are contained in all of these structures. Mass, stellar mass, is something that connects us more directly with simulations. So it's actually, it's quite important to bring closer the observers to simulators. I mean, this is something that is happening more and more, and this is an amazing thing that is happening, where we have there have been very many generations of simulations, but the new generation of cosmological simulations have been including also a very detailed treatment of gas, what actually happens to gas, instead of actually maybe slapping down recipes of what happens, just really a full hydrodynamical treatment. And we're starting to see, to reproduce with simulations many of the characteristics and morphological trends that are observed in galaxies. And this actually, this is taken from, whoops, sorry. Okay, yeah. Yeah, this is a work from Chaganel from the Illustris simulation. So here, just when I say full hydrodynamical treatment of this baryonic physics, this includes cooling of gas, star formation feedback, and AGN feedback. And this is just to show you a little bit. This is from the Illustris simulation, just showing you the gas content. And here you can actually see stars, but where these two are actually really truly related, where you have gas producing, being collapsing, changing its temperature, and producing the stars that we observe. So the intention, so that's for simulators. I mean, it's easy to get to the stellar mass. So you have maps of stellar mass. For observers, what we have is maps of light. So tricky to transform from light to mass. So what we do is we have over the years, I mean, astronomy historically and optical, also a lot of radio observations. But what we actually have come to understand is that we really need to exploit the infrared, where dust emission, where the dust does not block. I mean, it's quite transparent in the infrared. We already see this in the near infrared, especially in the mid infrared. And here, what I want to particularly point to you is the fact that the infrared luminosity, in this case, if you look at this, two images here of a globular cluster, you can see that in the visible, you don't see much of this cluster, but this actually lights up when you look in the infrared. So the idea here, it's not so much what I point to you here is not so much the dust extinction, but the fact that the infrared luminosity is actually dominated by old stars, low mass stars. And if you consider, well, any stellar IMF, excepting the top heavy IMFs, you actually see that the stars that have masses less than 1 solar mass really truly dominate any episode of star formation. So basically, and if you look at a very young structure, for instance, this Pleiades, you actually will see it light up in the optical. But when you want to actually trace the bulk of the stellar mass of a system, you actually go to the infrared. And this is just, I mean, the first one was more speaking through images, and here's speaking through plots. This actually is a very nice figure that was part of the driver 2016. This is the Gamma collaboration. And basically what you see here, it's just SEDs for galaxies. They're always all the same mass, all have the same stellar mass. And you have here the luminosity, the wavelength. So basically any difference that you see here, I mean, it's a luminosity. So this will actually translate to mass luminosity ratio. So your means of transforming light to mass, as I was saying, that was our purpose. But here, for instance, you're looking at different types. So these are late types in blue, early spiral types in green, and in red you have early type galaxies, ellipticals and lenticulars. You actually see that they have actually been made so that they vary a bit with age, metallicity, and extinction. Just the point here is that they're varying a lot, these SEDs, but the point is that you have very little dispersion in this region. So this region, I mean, you have, if you look in this region, you will actually have a very slight differences when you transform from light to mass, even if you're considering different ages, metallicities, and extinctions. So this actually is the graphical way of convincing you of the power of the infrared. And this was the motivation. I mean, this is one of a great motivation to use JWST to look at stellar mass distribution in galaxies, but this was already the motivation for this legacy mission, legacy survey during the warm Spitzer mission. So Spitzer did not have any more cryo to support the longer wavelengths investigations, but it was still possible to use the 3.6 and the 4.5 micron IRAC bands. And a lot of people became quite creative to actually run after this opportunity and create surveys that would really take advantage of this. So this was the birth of S4G. So this is the Spitzer survey of stellar structures in galaxies. The PI is Kartik Sheff. This data is already all public. So actually the S4G collaboration does not really exist anymore, but there were, I was part of that founding group, so that was quite fruitful. So here is just showing you to give you a sense of how deep we went. These are 2MASS images. So 2MASS is the near-infrared survey. So JHK from the surface of the Earth, I mean from the surface of the Earth telescopes. And here this was using Spitzer. So you can actually see these are the same galaxies, the same scale. So you just really have a very nice possibility of going and exploring the outskirts of these galaxies. So basically the intention, I mean, S4G was to create, well, yes, a survey in the infrared where all morphological types would be well represented. It was not exactly the case at the beginning, but this was completed afterwards. A deep imaging of low mass regions in the outskirts of galaxies and homogeneity in depth and data processing for the whole sample. So here we're talking about over 2,000 galaxies, basically just bigger, big, close, bright galaxies. And the motivation was really to have this possibility of transforming light to mass, motivated by the fact of this driver 2016 SEDs that I showed you, where that region, the mid-infrared between 3, I mean 2, 5 microns is a really sweet spot to actually look at stellar mass distribution. So our interest then, I mean, in general, we want to compare, we want to understand galaxy evolution, looking at light transforming into mass, so that we can actually compare to simulations. And there's actually, this is quite interesting. There's a lot of work that is presented here in this conference. I mean, to be able to actually distinguish what the different structures are, their different approaches. This is work here that I'm showing from Querejeta. This is from the FANGS survey that is a combination of ALMA data, MUSE data, and now JWST data. It's really a fantastic survey. So this is just a plot from their paper in 2021, where they basically just make the distinction between the bulge, the disk, and the bar. And this can be done in many ways, using Gauss-Fit, using morphometrica. We heard yesterday, we have different, by Amanda, we have different a means of doing this. And this is also just to show you a bit of the variability, the diversity in approaches. This is work by Galaxies Zoo. So this is from Karín Masters 2021, where they have actually, this is citizen science. Perhaps many of you already know Galaxies Zoo is a citizen science project. So basically you ask a lot of people that are not necessarily trained. They can be astronomers, it can be you. They're not necessarily trained to detect stellar structures or classify galaxies, and you ask them, you give them a small tutorial, and then you ask them to classify as many as they want. So this has actually been quite productive. A lot of papers have come out, but my interest here is just to show you that, for instance, here the person is actually asked to draw a region where they see the spiral arms, where they see the bars, and then they produce this kind of plot where you have a galaxy, and this is just depending, I mean, the strength, I mean, how dark the color is, depends on how many people classify that specific pixel as pertaining to one region or the other. So basically, this is just kind of like a visual way of separating galaxies. And if you see, yeah, just a moment. This is just, these are just posters from yesterday. I mean, this is posters from yesterday, so I have not seen the posters from that will be posted up from today on. But this is just to give you a sense of the different ways. I mean, we have decompositions, we have Gauss-Fit, we have unsharp masking, we have a lot of different ways. The 1 sigma just looking at the density in fluxes. I mean, these are a lot of students and also non-students that are, I mean, people, different researchers that are actually exploring how to actually make this this distinction between one stellar, the light that pertains to one stellar structure to the other. Because I have told you, we need to, the recipe to go from light to mass is this one, go to the infrared, but you also need to say which part of the galaxy pertains to which structure. And this is just a way of saying that mapping spiral structure specifically, because all of this is only spiral arms, is actually quite tricky. So what the S4G, they did, they used Gauss-Fit. I mean, Gauss-Fit, it was with an ideal wrapper. This was work by Salo et al. In 2015. What they did was actually take the original image and just decompose it into different components, including disk, including bulge, the possibility of a secondary disk, a nucleus, which just means point source in the center. Depending on the galaxy, this could be an AGN. This could be more likely, we're talking, I didn't actually say this, it was written, but I didn't say it. These are close by galaxies up to 40 megaparsecs, so we don't have wild AGNs there. So very likely it'll be a nuclear starburst. So that's actually, but from the perspective of this decomposition, it's just an unresolved point source in the center. So then you basically have the original image, so a bar model, bars, bulge, disk, the total model, and naturally, if you subtract it, then you retain in the residuals, you have spiral arms and other structures that were not included. They could be included in the model, as I just showed you. There are at least 6 people that are bringing posters here specifically to address how to define these spiral arms. But just this broad approach that was applied for this large sample did not include the spiral arms. So there's basically this is an invitation. I mean, when you actually start looking, and this is not the only place where this is being done. I mean, there's a lot of work that we have been hearing or we will be hearing about S+, JPass, what they're actually making this kind of work. And with the intention not only to look at the stellar mass distribution, but also stellar populations. So basically, it's just an invitation to undertake spatially resolved studies of specific galaxy structures. And there's a lot of work that has actually been coming out from the Timer survey that uses the MUSE IFU, biggest IFU around in the optical. And also we have actually been hearing quite a bit, and we'll be hearing some more about S+, which is a 12 filter survey, and doing this kind of work. There was one paper that was just accepted 2 weeks ago by Cirial Diaz, looking at the bulge bulge this decomposition. So this kind of work, I want to take you then specifically to some specific projects that are actually posted here in this conference. And here is just an interest that we have taken in looking at bars in massive spirals. And here is Yasmin, who is probably trying to hide as best as possible in the seat that she's sitting right now. But what she does is she actually looks at over 360 bars, and using this decomposition and just looking at only galaxies that are not too inclined, so that we can actually confirm also that we can trust the classification that it is or it's not a bar. What we look is actually at the content, the mass content in these galaxies. And in this case, what we see, just if you ignore the distinction, it's just a histogram of the bar to galaxy mass ratio. And you can actually see that it actually falls under 10 here. So it's under 10%. So it's like between 5-7% of the galaxy mass. But the interest here is actually to look also at the different components that we see in these galaxies. We have over 360 bars, so we can actually do this. And what she did was a distinction between whether the disk has a bar nucleus, a disk, if it has a bulge also, or if it doesn't. So basically here I have actually drawn this curves, but you can actually look at her poster 482. You can actually see that there's a distinction. I mean, these are galaxies that do not have a bulge, and these are galaxies that have a bulge in green and in orange. So the idea is that we have more massive bars in disks that have bulges. We actually extend to this work for massive galaxies. So galaxies with masses stellar masses greater than 10 to the 9. And here is looking at the low massive galaxies. So this work included Michael Grossi, who's a dwarf galaxy expert. And what we see is just, well, first looking at the proportion of dwarfs. I mean, galaxies, bars are less frequent in low mass galaxies than they are in massive galaxies. Just to give you a sense, I mean, 38% was what she found. I mean, it actually coincides with work that has been done previously by Peter Irwin, compared to 65% in massive galaxies. So these are just the bars that we see in dwarf galaxies. And if you actually look, and this is actually a plot that I grabbed from her poster, you can actually see that there's a distinction, slight distinction. It's not as potent, but we run statistical tests to make the distinction to see if they're actually distinct. They come from distinct parent samples. So basically just distinguishing here between galaxies with low masses, between 10 to the 9, 10 to the 10, because we do not have so many galaxies, especially bars at masses lower than that. So for the moment, I mean, what we're showing is this in blue, and in purple, you have more massive galaxies. And the idea is basically you have a more pronounced tail in this region here for more massive galaxies. So putting these things together, you have a low proportion of bars in low massive galaxies, and lower masses containing the bar structures in lower masses in lower mass galaxies. And also the bulge seems to be perhaps an indication of a more mature galaxy, just going towards the early type and showing more massive galaxies. So this actually is all consistent with the trend that all the bar forming action is actually happening in the low massive galaxies. So the low massive galaxies are on the one hand acquiring the conditions, and when they have acquired the conditions, they're slowly building up those bar masses. We have actually brought this because the connection, I was motivating the connection to be able to have observations talk to simulations. So we have actually started looking at the TNG 50, looking at the BART sample from Rosas Guevara. So there are 150 galaxies, but this, so here shown the different masses displayed. I mean, they have actually lower masses also, masses less than 10 to the 10. They were just not, they're not published, but I mean, they're there. And we actually looked at specifically just, this is an example of a strongly barred galaxy in TNG 50. And we undertake the same decomposition that we just did for observations. I mean, that's the intention. We haven't actually performed that yet. So for the moment, what we did was use, I mean, we have stellar maps from the simulation, and we just take the typical thickness of a bar, typical. We have taken actually a word. I thought I had put it here. Sorry. Is it here? Okay. A 5 kiloparsec tall, basically the height. And just taking the median shape, the median extension of these bars, and we actually find a bar distribution, a bar to galaxy mass ratio that is in the ballpark of what we find for observations. So this has actually been done quite roughly, but this is basically a conversation that is starting between observations and simulations. So we find here, this is a work by Chao and other Pias, and what he finds is between 1-3% compared to what we find with the Spitzer survey stellar structure that is around 7%. So basically, the next thing is to actually do this more carefully. And then now to just getting closer to the end, I mean, the intention is to look at stellar maps, but we actually also have, I mean, many things that we do to understand the shapes, to connect the shapes with the processes, astrophysical processes that have led to the stellar distribution that we observe, is actually to look at the make a connection with the stellar population that we see, the stellar populations in this structure. So here, I mean, the main thing to start with is that bars are stellar structures. They're typically dominated by old stars. And if you actually look at a bar galaxy out to the UV, you actually lose track of that structure. And this is work that actually was just accepted a couple of weeks ago. It should hit the archives pretty soon. It hasn't yet, but it was accepted by MNRIS. What we actually look at is the LTC profile as a function of just at the profiles with the radio profiles. And what we see is that galaxies, as you look at them from the infrared, which is the more, would you say, base mark, a way of looking at the distribution of lower stars, low mass stars. When you look at them towards the blue, they actually become thinner and longer. Just to exaggerate a little bit the effect, this is what we see. And it can actually depend on whether you're comparing one band with the other or even extending to the NUV. This value can actually increase up to 20%. So basically what we attribute the fact that we're seeing longer bars and thinner bars. And when we say a thinner bar, this is something that is also, that can be connected to the strength of the bar. So if we're actually comparing an observation of low redshift bars with high redshift bars, and we're using the same filter, band shifting, I mean, the universe is expanding, so we're actually looking at bluer the bluer rest frame wavelengths. So we can actually be mixing a bit the conclusion of that bars are getting thinner or longer because of this band shifting effect. So basically what we attribute part of this conclusion to the way that we measure. We make these measurements. Why longer? Well, star formation knots in the ends of the bars are very common. So in B band, they will actually become more prominent. So this will actually push out the ellipses that are feeding the isophotes. And this will actually make the bar longer. On the other hand, the bulge, which is more typically associated to older stars, it will actually become less prominent in bluer bands. So this will allow to actually fit thinner ellipses, making the bar appear thinner. However, there has also been quite a lot of work from the timer and from other, looking at UV emission in these bars, attributing part of this effect to younger populations. And what we actually did, we started a collaboration with Rubens Machado. I see that there's a student of his here. This is work from undergraduate student, looking precisely at that, just looking at the TNG 50 stellar mass maps and looking at the bar when you only focus on older stars or younger stars, and actually showing that when you look only at the old stars, you do actually see slightly shorter, broader bars. When you compare to the younger stars, you actually see thinner. So this is not only the way that we measure things, but actually is associated to the kind of populations that we're looking at. So beware. Morphology can be tricky, depending on what band that you use. It can be tricky. We know this, but it can be, it's important to establish these benchmarks for the exploration of higher redshift. So basically this work, the intention is that it allows us now to measure intrinsic changes in bar structural parameters at different cosmological times, making these considerations and corrections. And this is something that has been done, I mean, looking at simulations and I mean, not this part that has been done, but the work to start looking at bar properties and our intention, our interest to look at bars in disks because they tell us so much about the disk maturity and their bar properties. This is work by Tae-Young Kim using the HST-ACS data, just looking at the length of bars, and there does not appear to be much of a evolution when the bar length has actually been normalized by the galaxy size, and this work is in the simulations. Just also looking here, you can actually see the different histograms represent the different redshifts, actually showing that there's no a clear evolution of the bar length. What they do show here is actually perhaps a dependence on the disk size. And here I actually pointed to IRI 2023, or also Virginia Cuomo's poster. So actually speed through, basically, this is just a lot, this opens a lot of possibilities to do a very exciting work with JWST and actually start comparing and looking at the predictions from specific isolated galaxy simulations that show how the growth of these bars could be. And NIRCam actually does allow us to do this already with these galaxies that for the moment we're just detecting these bars. So I'm going to rush through now, not rush through. I'll just succinctly speak of the rest. Basically, the idea here is to point to many surveys that have come out that are composed of just a myriad of filters. There's S+, J+, J+. We're actually been hearing a little bit about this. We'll hear some more, certainly. And with this intention, we actually have started in Valongo, the census of Austral nearby galaxies. This is actually going after the S4G galaxies that we can see from the south and really just going quite deep. We're actually going over 3 magnitudes deeper than Sloan in the GRIZ bands with the SOAR telescope. This is just an image showing students at work. And we actually do go deeper than other surveys, depending on the bar. I mean, we actually are trying to go to the same mass surface density as S4G. So going down to 1 solar mass per parsec square. And these are just the kinds of maps that we're putting together where the stars are forming, just star formation rate maps and stellar mass maps. And we have actually been, many of the posters that you have here, and we have 16 posters from Valongo, no, 4 talks and 12, so there's a lot of interesting things that are going on here. Not all of them are about galaxies, but just I wanted to point you to very interesting work that has been developed by Yana, Raisa, and Yaira, and Yana and Yaira are here, making a connection between these galaxies and astrochemistry using PAS, so polycyclic aromatic hydrocarbons, specific details regarding their sizes, their sizes, their charge, their composition, chemical composition, to actually tell us something about the agents. So I invite you to go and check their work, and also look forward to Nathan's talk, also going after these Kanga galaxies, but using H1 to actually look specifically at Milky Way analogs and look at the dark matter distribution in these galaxies. And we have actually been moving forward some of this work also with TNG50 to understand dark matter distribution in Milky Way analogs. So with this, and actually getting really nice coincidence, consistent results of the local dark matter distribution in the Milky Way when we compare to the dark matter distribution at the position that would be equivalent to the sun's position in other galaxies that are Milky Way analogs. So basically just this is an invitation to explore. Galaxy shapes are not just pretty pictures, they're very intricate, detail-rich data sets that can be used to tell us something about the past events and construct galaxy evolution. We know this, we've been working on this for a long time. The conversation has been going on for a long time between simulators and observers, but this conversation continues to be needed to be strengthened. The S4G data in the mid-infrared are available on IRSA for everyone to use. This is, I mean, if you want to see some, get in touch, please do. And just to leave you with a message that we have postdoc positions available like right now. So talk to me, not now, but in a moment, talk to me. So if you think you can deal with living in such a beautiful city as Rio de Janeiro, then come and talk to me and we can chat about possibilities. Thank you very much.
Questions, Vladimir?
Thank you very much for your very nice review, Karín. Just a few comments, a small comment about the simulations. You mentioned that in the TNG50, the bar fraction apparently is lower than in the observations. Just a warning, because in simulations, the bar formation is a process that depends on the vertical structure of the disk. So we need to resolve at least with the thickness of the disk. I think TNG50 doesn't attain in many cases this resolution. So we also have in several simulations, we don't have bars, but when we simulate with more resolutions, already bars appears. Yeah. So this is a rule of thumb that the resolution should be at least higher, larger than the thickness of the disks. Yeah.
Thank you. Thank you for the question. Actually, I may have misspoke. Simulations, I mean, there's some contention. Simulations are actually showing that there are bars at a higher redshift, at redshift 40 and G50. The work by Villalba Izquierdo, by Rosas Guevara, they actually show higher fractions. So even this very exciting news that came out on Nature, I mean, the simulators were like, okay, we kind of knew that there were bars there. You are right. Certainly, there's a definition because observationally we talk about spirals or disks. I mean, they actually look at the presence of a thin disk, try to look at. So certainly, you're absolutely right that for the need of this resolution. But actually, something very interesting that I didn't even mention because I don't know that much what to do with it, but that simulations, at least TNG50, is showing a decrease in the bar fraction as we go on to, like a slight peak and then a decrease for today. So it's kind of, the suggestion is that maybe these are somehow acquiring conditions that pushes them out of the sweet spot to form bars. So there is still some contention on the bar fraction. But yeah, certainly you do need the resolutions, but simulations are actually, I agree, simulations are finding also that that you have bars, many bars that are forming at higher and higher redshift. Yeah, this has been going on in the last couple of years, but you're absolutely right. Resolution is key.
Otra pregunta.
Thank you, Karín, for your nice review. It seems that there are a number of galaxies which are not exactly like the simple picture and have, let's say, two spiral arms starting from each end of the bar. And many people believe that our galaxy is like this, let's say, and this would explain why we have four spiral arms in the inner part. Do you have an idea if this is, let's say, very rare, or it is you can connect it with the age of the bar or with the mass of the bar or things like that?
So it is my understanding that, I mean, it is commonly associated. You have the bar knots at the end of the bar, and you have spiral arms coming out of them. Actually, the galaxy, one of the arguments to favor the existence of a bar in this galaxy. Sorry. So this is at redshift 4. It is that when they actually look at only if they take out a Forero model for the bar, there's a spiral arms coming out from what would be the ends of this structure. So my understanding is that usually you do have that configuration. Whether that, I haven't actually looked at, perhaps there have been some work. I think you would know if there has been some work on this, Jacques, but I'm not sure what our understanding is specifically on whether you have the spiral arms coming out from the knots or not, if this is associated to the age. I mean, it seems to be a good question. I don't actually have an answer for that. I do know that there's certainly deviations from what I'm showing and from what our picture of a bar. You sometimes have bars that are offset even from I mean, the disk seems to have an offset bar. I mean, we actually see this with, I mean, it's not super common, but we actually see this, but I don't know exactly what would be, but it seems like an interesting connection to exploit.
Thank you.
Muy bien, estamos cortos de tiempo, así que los invito a continuar la discusión con Karim en el coffee break. Agradecemos a Karim.
La primera es la, sí, está.
Bueno, le damos la bienvenida a Jaime Forero Romero. Él es de la Universidad de los Andes y nos va a hablar sobre Mapping the Universe with Galaxies.
Thank you, everyone. Good morning. I'm going to start with some good news. So by now, as November 2023, DESI has gathered more extragalactic spectra than all past observations combined. As a number, we have now 27 million extragalactic spectra of individual objects. But what is DESI? Why we are chasing so many spectra? And why do we think that this is a big success? So DESI stands for the Dark Energy Spectroscopic Instrument, and DESI is the latest stage of a progression of 40 years in large spectroscopic surveys. So let's start here. 1980, CFA survey, it gathered around a few thousand galaxy redshifts. If we go to the 2000s, we have the very well-known SDSS project. And when it was progressing, it was gathering at its peak a few 100,000 spectra, redshifts. Then the next generation BOSS, by the end of the last decade, gathered around 2 million spectra. And the goal with DESI, when it finishes in 2026, will be to have at least 40 million spectra. The next generation, here is one example. This doesn't exist yet. We have Mega Mapper for the US-led experiment, but there are similar experiments planned in Europe and China. But the goal will be to have 500 billion spectra. And if you take a look at this linear scale here in time, and if you take a look at the logarithmic scale on the y-axis, you see that the growth is exponential. Every 10 years, we have one order of magnitude more spectra. And the nice thing about this exponential growth is that basically, once you start a new survey, you really don't want to keep the other galaxies, the other spectra. Basically, you can start and measure again. In DESI, in the first 2 months, we measured 2 million spectra, which is basically the whole history of extragalactic spectra in only a couple of months. This is the early revolutionary groundbreaking paper from the 80s. This is data from the CFA survey. And the way we usually present this is that we are here, we, the Milky Way. We have right ascension. And this is a thin slice in declination. And every point there corresponds to a galaxy. And the radial coordinate corresponds to radial velocity. And if you pick a value of the Hubble constant, that would mean you have some distant measurement. And what was groundbreaking at that time is that we finally had observational proof that galaxies are not distributed in a homogeneous way. We have something that we call now voids, regions without bright galaxies, at least in the limit of the survey. We have something that we call filaments, and we can have something that we could call groups or clusters. In the picture we have today of this cosmic web, there is another element called a sheet or pancake. So basically we have 4 elements: voids, sheets or pancakes, filaments, and clusters or groups or peaks. So this is the 80s version. We love the 80s. And now this is the 2020 version. This is the same kind of plot. We are now here. And now take a look at how deep it goes in terms of distance. This is a 1500 megaparsec. And now we have a few million galaxies in this plot. But again, the important part here is that the cosmic web is a persistent structure in the large scale structure of the universe. And what the experiments are doing now is basically going further back in time, but also having a denser sample at lower redshifts. To appreciate why this is groundbreaking, these results from DESI, let's take a look at how it was done before. And before, I mean SDSS and BOSS. You had to have a human plug in optical fibers into plates. Then you have to take the plate with optical fibers to the telescope, point the telescope, and if you drill the holes correctly, you have the light from the galaxy into the holes, into the fiber, to the spectrograph. And roughly you have 300 fibers. And you do it all over again for 10 years. And after 10 years, you have 2 million spectra. If we wanted to do the same thing with DESI, with the same technology, and get millions of spectra, we will have to do this for 20,000 years. But we have to publish papers, we have to get jobs, so we cannot do it that way. So there are 3 main aspects that are helpful to the success of DESI. And the first one, robots. We replace humans by robots. This is the focal plane in DESI. And here you see small robots. Each robot has an optical fiber at its tip. And what is happening now is that every time you take exposure, every half an hour roughly, you move the robots and then you are taking light from different galaxies. So no humans involved in plugging fibers. So robots, the first key. The second key is having a larger telescope. This is a larger telescope than the one used for SDSS. This is a 4-meter class telescope. This is the Mayall telescope in Kitt Peak in Arizona. So of course, if you have a larger telescope, you have shorter integration times and you can go deeper. And the third aspect that is very helpful in DESI is basically artificial intelligence, but I will go deeper into that afterwards. I want to now take this conceptual view of what we are doing. From if we take the point of view of someone running a simulation, we start with some initial conditions, matter distribution, the amount of matter, or matter and energy contents, and then we assume some physics that are going to evolve these initial conditions into the present. And into the present, we have now the cosmic web, as seen in simulations. We have the voids, we have the filaments, we have our clusters, and we have our sheets of matter. If you change the initial conditions, or if you change the physics, the cosmic web will look different. So what is happening now is that basically the cosmic web is encoding the information of the initial conditions and the physics. And the whole work here is how to decode that information, how to extract the information from the observed cosmic web. I don't have enough time to make it to make a proper review of why this is really important. But one of the cornerstones in cosmology and how to extract information from the cosmic web is what we call the two-point correlation function. And this is basically giving us a measurement of how clumpy is this galaxy distribution. And most of the work that has been done in the last 40 years use a version that is called the isotropic correlation function. This basically explains why Peebles got his Nobel Prize, basically by establishing the two-point correlation function as a robust tool in physical cosmology. Why robust tool? Because you can apply two observations, two simulations, and from theory, if you have a theory of the matter energy content of the universe, you can predict more or less what correlation function you expect. So you are able now to compare theories against observations, against simulations, and constrain cosmological parameters. But the cosmic web goes a bit further, because the cosmic web, what we see with our visual perception, is actually anisotropic. Anisotropic. So the two-point correlation function doesn't really capture what is happening in the full richness of the cosmic web. What we have here is the result of a comparison project that we ran a few years. So we were a bunch of theorists. We took one cosmological simulation as an input. The scale is a couple of 100 megaparsec. And with the same input, every group decided to run its algorithm to find the cosmic web. So in white, you see what I find to be voids. In green, the sheets. In blue, the filaments. And of course, you can see this is also very popular algorithm, disperse. And you have different algorithms. And you wonder what is happening with this algorithm and with this one. And the goal was not to say which one is correct, because we know why we have the difference there. The difference comes from the scale that your algorithm is taking. Let me explain a little bit more that. Every time that we use one of these algorithms, implicitly or explicitly, you have to put a grid on your data, and that grid is going to fix you some scale. That is not really physical, it's a scale from your algorithm. So basically what is happening here is that those algorithms are probing different scales of the cosmic web. But what is interesting is that now you have a tool, many tools, in fact, many algorithms, to say whether a dark matter halo or galaxy, if you have a survey, is a galaxy sitting in a void, in a filament, in a sheet, or in a cluster. What kind of questions we want to ask with this tool? Let me summarize these questions in two families. There is a family of questions that we want to address in terms of whole populations of dark matter halos or galaxies. And the first one has to do with alignments. Why alignments? Because this is the most salient feature of the cosmic web, the anisotropy. So in this very specific example, we take a look at the alignments between the cosmic web and the halo shapes. Dark matter halos are not spherical, they are ellipsoidal. And there is a signal that you can pick up there. For people doing weak gravitational lensing, this is noise, so they want to have this background to get rid of it. But some other people, this is signal that if you happen to measure this correlation strong enough, probably you are confirming or disproving the expectation from lambda CDM. So take a look at this plot here. This is the most interesting one. So here we have halo mass from 10 to the 9, 10 to the 12 Milky Way, 10 to the 14, 10 to the 15 cluster masses. And we have here the degree of alignment. If you are around here, there is weak alignment between the shape of this halo and the cosmic web. And the strength is a function of the mass. And the strongest signal is coming from clusters. Clusters are the most elongated structures, or are also the most aligned with the cosmic web. Why is this interesting? Because if you're doing cluster science, probably you want to probe, test lambda CDM by comparing degrees of alignment in clusters and its neighborhood with the expectations from lambda CDM. So that's why we did this work on simulations. Another type of question that you can ask then now that you have the cosmic web is for individual objects. In this case, we have the local group Milky Way, Andromeda, M31. And we go again in simulations and we find analogs of the local group, meaning we have two dark matter halos with similar mass, distance, kinematics, and isolation. And we ask the question, where are we living in the cosmic web? What we have here is mass of these two halos, basically a total local group mass. This is the most probable range of the local group mass. And what we see is that most likely we are living in a filament. Fine, we live in a filament, all right, most probably. But then if you take a look at the simulation, if we live in a filament, this filament is connecting the Milky Way and Andromeda. If Andromeda is here, the Milky Way is here, the filament goes in this direction. If you take a look at the simulation, then you expect that the satellites will fall along this filament. But if you know something about the Milky Way, you know, for instance, that the classical 11 satellites of the Milky Way are not in the direction of Andromeda, are almost perpendicular. So the question that we had at the end of this paper is the following: is the local group atypical in lambda CDM in terms of these alignments and isotropic correlations that we find in terms of the cosmic web? So let me move forward to DESI. One of the elements, I mentioned two elements for the success of DESI. One was robots, replacing humans by robots, by machines, the whole history of human labor. And then having a larger telescope, it helps, of course, but then also it helps having more sophisticated tools for data processing. And more sophisticated tools for data processing means using AI. So let me define AI in this context. Any technique that mimics human behavior, I will call AI, anything, all right? This is a very general definition. As a subset, we have machine learning, where these techniques have to use statistical knowledge. So now I'm making it more specific, because I have to learn from the past to predict the future if I want to do that. And a subset of that is deep learning, because I'm going to get the statistic using a particular architecture for, let's say, my deep convolution neural network. So there is a subset of that. So in DESI, artificial intelligence helps us to define the targets. We have to place the fiber somewhere, but where are we going to place the fiber? We have to define the targets. In DESI, there are 4 main classes of targets: nearby galaxies, luminous red galaxies, emission line galaxies, and quasars. But on top of that, there are some secondary programs. You can think of them as secondary projects. And one of those is trying to gather a complete sample of very low redshift, less than 0.03 in redshift, going down to 10 to the 7 solar masses in stellar mass. So those are faint objects. If you try to select those faint objects only using photometry codes and color codes, you are going to have a lot of contamination of high redshift objects. So what we do in this case is we use images, the images themselves, and of course, some other spectroscopy that we have to train the convolutional neural network. I have a good selection for those low redshift, low mass galaxies. This is one example of how AI goes into target selection. I love this one because this is more related to really replacing a human, and replacing a human in the good way. One aspect of running a survey is making sure that everything is working out properly. And sometimes this involves doing visual inspection. So you take the data, you reduce the data, and at some point, a human has to look at this spectrum and say, does this look okay or not? But with DESI, in a good night, we get 100,000 spectra, let's say. Then 100,000 spectra get picked during the night. Then the supercomputer is running in California, and then we distribute the data. We call it redshifts by breakfast. So you are having your breakfast, and you are taking a look at 100,000 spectra. You're having lunch, you're having dinner, and you didn't finish taking a look at the spectra. So that's why John, he was a graduate student at Universidad de los Andes in Bogotá. We devised a method to do this automatically. And basically, the key concept for machine learning that we implement here is dimensionality reduction. So each point is a single spectra, but this spectrum lives in high dimensions, every point for the flux. So let's say you have 100,000 galaxies. each galaxy living in a high-dimensional space, but then we use UMAP, a manifold approximation, to represent each spectra as a 2D point. These are arbitrary coordinates in this computational space. And we see galaxies clumping together here, stars, quasars, but then we have sometimes outliers. And the outliers we find there in this reduction of dimensionality are not very cool objects. They usually are some kind of failure in DESI. Usually something happened with the CCD, some physics died out. In this case, I believe the failure was that a very bright star fell into a fiber and the light contaminated the neighboring spectra in the CCD. So this is why we have this, basically this is contamination from another star. But this helped us very much in 2021 when we were doing survey verification, science validation, to find mistakes, because it was the first time that the experiment was running. So it was very useful to have this kind of probe. And of course, artificial intelligence to define the cosmic web. So now what we are trying to avoid is using a grid. I was telling you before, if you are in a simulation, you have to grid the data, you define a special scale, and then all your results depend on that scale. Then what we try to say is forget it, let's just use the data as we have it in 3D, and instead use a different data structure that is a graph. Now we have a graph, and from the graph, we train it to predict the cosmic web as defined by other algorithms. But as we will show you later, basically, we could do only with the graph. It will be really enough. So what is the next frontier for us? We are having a new cosmic web definition. So this is the list I showed you before from this summary paper, probably the most, from what I've seen in some of the talks here, disperse is one of the most popular ones. The limitation of sparse is that it can only classify galaxies into 3 of the 4 web types. And the limitations of all the others is that they have to use a grid. So the new algorithm that we call Astra is algorithm for stochastic topological ranking. It only uses the graph. It works on survey data without any grids, and all 4 web types are identified. And what we are doing with that is combining this cosmic web classification with the anisotropic correlation function. What we do have here are the monopole and the quadrupole as a function of moving distance of different cross-correlation and self-correlation functions. So for instance, let's take a look here. We are here cross-correlating filaments with voids, and this is the expected signal in the monopole. Here we are cross-correlating filaments and voids, and this is the expected signal in the quadrupole. This is on the SDSS data. But what if we wanted to constrain cosmological parameters? What do we have to do? We have to do one of 2 things. We have to have a theoretical model that predicts the results for those functions that we have here, or we could use a lot of simulations, convert those simulations into SDSS-like data, and compute the same statistics, and do some kind of chi-square between the 2. And the lowest chi-square is going to give us, or we are going to say, the most probable value for, let's say, omega mater or omega lambda. So it involves some kind of comparison. But the interesting part is that this is very rich now. This is very rich information that we're extracting, combining these 2 probes, the cosmic web classification and the correlation function, now the anisotropic correlation function. We now, in the group, we love using graphs because it adapts naturally to the structure, to the spatial structure of the data. So we are now combining neural networks that we learn to love and use with graphs. So this structure is called graph neural networks. And what is the difference between a traditional neural network and a graph neural network? The traditional one, you have this fixed structure between layers and connections between layers and neurons. But what is new in this graph neural network is that the structure, the connection now follows the graph itself. So you give the graph, it's going to give naturally the structure on how to pass information in your network. People were experimenting with that a few years ago, and it's been proven to be very useful. How are we using that? In what context? We are using that to have as an input, let's say, photometric properties of galaxies and the position in the cosmic web to have more precise predictions for the stellar mass. Of course, what we are doing behind that is that we have the full spectrum. We have to do beforehand some kind of fit with different quantities, different techniques to get this, the stellar mass. But at the end, what we want to have is just give me the cosmic web, give me some magnitude, and I will give you the stellar mass. This seems to be working. These conclusions are mostly for the young generation. Who is the young generation? Anyone who was born when the surveys started in the 80s. So let's say who is, by a show of hands, who is 42 years or younger? 42 or younger. Show of hands. Great, this is for you. If you are older than 42, I'm sorry. So you are young enough to include the cosmic web into your toolkit if you want to better understand galaxy formation in a cosmological context. Or if you want to do cosmology, please take into account the cosmic web, the anisotropic information. Sorry. DESI. If you like SDSS, you are going to love DESI. That is going to be public as well. Slowly, but surely, all data will be public. Graphs. Stop binning your data. Stop making grids. Use graphs directly. Now we have a whole new set of tools on GitHub everywhere to handle graphs and handle large number of data points. So don't be afraid and start using graphs. And there is a trend in astronomy, probably you have realized if you are from the younger generation. There is a transition between, let's say, individual PI doing studies of some objects to large groups running surveys. So please, at least if you are young enough, be ready to participate in this context of large collaborations and doing surveys. Just be ready to do that. And finally, of course, we have also seen that in many talks here in LARIM, you have to have some working knowledge of AI to be able to make an impact, a contribution in your whatever field you are doing. It's not a choice. You have to know a little bit. And this is not enough to have an impact, but actually it's almost the minimum to start working now in astronomy. Thank you very much. I'm ready to take your questions.
Tenemos tiempo para un par de preguntas. Toma.
Okay, so although I agree with you that AI is a very important tool these days, it has to be said that these tools have the limitation of not producing any statistics at all, right? So we have absolutely no understanding of how Gaussianity is propagated through these tools, right? So it's a hint, but assessing what you just said, right? Evaluating cosmological models is completely impossible at this stage, right? So that's a very important warning to the young generation as well, right?
Yeah.
So understanding Gaussianity comes first. Understanding causality in the cosmological models comes
Understanding
first.
linear algebra comes first.
Exactly. And then we can talk about AI tools.
I agree. So I'm not advising that you do AI when you are 7 years old without doing all the things first. So there is a progression to follow. I completely agree with you.
¿Otra pregunta?
Hello. I want to know how you train the graph And then I didn't understand if, because afterwards you talk about some properties, you also include properties. Because if you, I don't know if you assume lambda CDM, but different cosmological models would lead to different structure, cosmic waves. So I don't know how you include that in the training.
So in the training, so the goal is to predict stellar masses. So we have the spectra, so we have to have some distance measurements. So there is an explicit cosmic model to translate redshifts into distances to get the stellar mass that I'm going to use to train. So this is a first part to your question, right? So there is an assumption in this specific project of stellar masses. But I don't know whether you had another question on how this is technically done, or?
Because I understood that you are using graph to find the
Exactly,
cosmic
so
wave,
exactly, so the graph.
structures. But this, so my question is, how do you train that? Because in different cosmological models for the
Correct.
for our or lambda CDM,
Correct.
you will have different
Correct.
structures, and then if you are training with an assumed model, you may be biased in the results in the cosmic wave that you will derive.
Correct. So basically what we are doing is we are training, so you have to fix a cosmological model to be able to build the graph, get meaningful, somehow meaningful stellar masses that you have to get from different methods. But in the process of training, we are changing basically stochastically changing or exploring different cosmological parameters to see how robust is this graph, let's say, the graph itself, the structure, the 3D structure, to those changes in cosmological parameters. But basically, it evolves in running this many times. Expensive, but the computer is going to do it.
Disculpen, se nos acabó el tiempo. Los invito a continuar haciéndole preguntas a Jaime en el coffee break. ¿Un anuncio?
Bueno, agradecemos a... Bueno, no me tienen que recibir con esos aplausos. Algunos anuncios, saben que el grupo 1 de pósters se tiene que bajar ahora, ya, y ya del grupo 2 pueden estar subiendo los pósters que van a estar hasta el final de la conferencia. Segunda cosa, la foto oficial del Congreso va a ser hoy al finalizar la jornada de la mañana a las 13:15 en la explanada de la Intendencia, o sea, todos salimos y nos ponemos mirando hacia arriba, hacia acá, en la explanada, y vamos a tener unos fotógrafos desde arriba, así salen todas bien las caras. Lo tercero es que el bus, para lo que tienen el bus contratado, sale a las 14 horas, también de la explanada. Está todo vendido, así que ya no tenemos ticket para el bus. Los tickets de la cena todavía quedan unos cuantos, así que les pedimos por favor que lo concreten en el día de hoy para poder pasar el número y también para ayudar a la organización, porque si no vamos a quedar con una deuda grande con el catering de la cena. Y bueno, por último, la reunión de sociedades científicas que vamos a hacer con representantes de cada una de las sociedades. Nos juntamos a las 11 acá a la entrada y yo los conduzco a este lugar. Y mañana vamos a tener la asamblea tradicional de la reunión en la cual, bueno, vamos a tratar algunos temas y en particular resolver la nueva sede para la próxima reunión latinoamericana. Era eso nada más. Gracias.
Muy bien. Ahora es para mí un placer presentar a Alejandra Melo, que viene del Max Planck y nos va a hablar sobre Strong Lens Search through Deep Learning with both ground-based and space-based imaging data.
Gracias. Primero quería agradecer a la organización por invitarme a dar la charla y poder presentar mi trabajo. So now I will switch to English. I'm Alejandra Melo. I did my PhD at Universidad de Valparaíso, working with Verónica Mota. And then I moved to Garching in Germany to do the postdoc at the Max Planck Institute for Astrophysics, working with Sherry Suyu. And alongside these collaborators that you see there, among others, I'm going to talk to you a little bit about the project that we have been developing, which is trying to search for lenses using machine learning, but combining the images from ground and also from the space. So before I start, I will give you like a very brief introduction and motivation as to why we are doing this lens search. So we have seen in the last 10 years that there has been a discrepancy between the measurements of the Hubble constant between the local distance ladder that are based on the Cepheids distance scale, and also from the ones from the cosmological model of the cosmic microwave background. So this tension has caused scientists to start to look for new ways to measure the Hubble tension. And one very direct and independent way to measure this Hubble tension is using gravitational lensing. So gravitational lensing, if this works, and gravitational lensing then describes how the light rays from a very distant source are deflected due to a very big, massive galaxy that is acting as a lens. And these light rays that comes from the back then are deviated by this big gravitational potential that come from several images. These gravitational lensing are very important. And if you came here for yesterday's sessions, there has been several talks about gravitational lensing. But more or less, these are some of the, some of the things that we can do with gravitational lensing. We can observe the very distant sources. We can also probe the distribution of the matter in galaxies and clusters of galaxies. We can study the AGN and also the internal structure of an AGN, obtain the black hole mass, and also microlensing, etc. But we can also, apart from all of these, we can also measure the cosmological parameters. And to do that, then, if we have, as I said, all of the light rays that comes from the very distant source that are being deflected, arrived at different times to the observer. So this arrival, the difference that they arrive to us, they are called time delays. And this time delay, if we combine it with a Lensman's model of the lens galaxy, we can obtain then a way to measure the Hubble constant. So to measure then the Hubble constant, over here we just need to measure a very good time delay, and also to measure the Lensman's model of the lens galaxy. And this idea was first proposed by Repsol in 1964, but he proposed it using supernova as the lens sources. But it was first implemented using quasars by Holy Cow. So Holy Cow, or the H0 lenses in Cosmocryos Wellspring, measure the Hubble constant from 6 joint gravitational lens quasars, as you can see there. The time delays were measured by Cosmocryos, which took light curves of these quasars so that they can obtain then the time delays. And they also obtain the mass model using a software CLI. So the joint likelihood of these 6 gravitational lens quasars then give us our H0 of 73.3, which this means that combining this using a flat lambda CDM cosmology, they obtain an H0 of less than 2.4% precision measurements. Now this H0, it is in well agreement with the one obtained by SHOES or the supernova or by the nearby universe, but with Planck, it has a 3.1 sigma tension. So not only we can obtain, as I told you before, and as Refstal said, to obtain the Hubble constant by lens quasars as the source, but also using supernova or strongly lensed supernova. In a strongly lensed supernova, it's the same as having a quasar as the background source, but instead of a quasar, we have a galaxy. So when a supernova then it's detected, we can detect the other images, for example, here of the supernova, and they also arrive at different times. They have several advantages compared to the lens quasars. First, they also have a very accurate lens modeling. The second, and the very most normal, is that they have a very simple light curves. Compared to quasars that we have to monitor them for months, many months to try to obtain the light curves, the supernova, they just obtain a very simple light curves. Normally, the light curve of a supernova, when we have a galaxy lens, is more or less weeks or months. And if the lens galaxy is, for example, a cluster of galaxies, more or less takes months to some years, but it's very simple. And also, they are standard candles. So it's pretty much easier to do it with a strongly lensed supernova. And after the Refstal that proposed these methods in 1964, it took almost 50 years to obtain the first image of a strongly lensed supernova. The first one by Kelly in 2015, the supernova Refstal, that it's the famous image one over here, which was obtained, the lens was a cluster. And also the last one was obtained this year, which is called Supernova Hope, where we see the lens also as a cluster. Now, all of these supernovas have been obtained from the different surveys. And as you can see, not all of them are galaxy, not all of them are accurate to obtain the Hubble constant. They are detected by chance or serendipitously, and they're very difficult to find. But right now, with the new telescopes that are coming by and with the White Survey, we will have much more chances and higher strongly lensed systems where we can obtain them and we can observe a strongly lensed supernova. And given this boom of these systems, the Holy Smokes project was created, which was to obtain then this the H0 from the strongly lensed supernova. So now what they do in Holy Smokes then is using time delay cosmography with the lens supernova to try to obtain H0. But not only that, they also try to study the supernova and the physics of the supernova. Because as you see, the supernova, when they explode in a lens system, then we can do a lens model to try to see and obtain more or less the time when the other supernova explodes. So then we can study the supernova physics or study the supernova progenitors, something that it wasn't able to do before. Now, they're also in this group. These are the Holy Smokers that we are right now, where the PI is Sherry Suyu. We are more or less the three more biggest teams that we have. First is lens search. So we are trying to find all of the lens galaxy lens systems so that maybe a supernova can explode. They also do a rapid modeling because, as I told you before, when one supernova explodes, we have to be fast enough to do a modeling so that then we can observe the other supernova explode and we can obtain the time delay very quickly. And third, they also study microlensing and time delays, and especially from supernova type 1A. If you want to know more about this, you can also go for the first paper of Holy Smokes, which is from Sherry Suyu in 2020. And there are like 11 more papers about this work. So as I told you before, they're been very rare. We can just count supernova with our hands, but with the upcoming White Surveys, especially with the Euclid Analysis T, the forecast for detecting new strong lens systems, it's 10 to the 5 or 10 to the 6. So we have a lot of data, and to detect also lens systems, it is difficult because we need high resolution images to try to see if there are not lens systems. Also, we need the wide area survey so that we can search in all of them. Oops. And also we need the confirmation of this system, so we need a spectroscopic confirmation. So with all of this data, there has been like automated ways, especially with machine learning, to try to detect these lenses. And one of them is using CNN, which in the last year has been very famous in the lens community to try to observe and try to detect all of these lens systems from different surveys. So right now, this is not the first time that it's made. There has been many in Heliosmokes and also by many others using different systems and different methods. But what we are trying to do right now with my group is trying to see if using the colors, for example, from LSST or from the legacy survey, it's enough to observe, or if we combine it also with a high image resolution, for example, HST or Euclid, it could be better to observe this or try to detect these lens systems. So for now, to use CNN, we need a survey first to try to search for these lens systems, but also we have the disadvantage that there is not enough lens systems. So we have to create them, or have to create mock lens systems to try to train the network and say, okay, this is a lens or this is not a lens. And I want to explain to you in a bit how we do that. And then we do apply the CNN, something that it's also like, but that we rely very much using the CNN's machine learning and deep learning, at least for lens search, is that we rely too much on visual inspections. So we do have a lot of false positives, and we need the human to search for the lenses, grade them, and say, okay, this is a lens or this is not a lens. So I told you before that sorry. So now I'm going to talk to you a bit about the work that I'm doing there. So I already told you a bit, but we are trying to then search for a strong lens through the deep learning with images from the ground and also from a space, simulating what is going to be LSST and also Euclid, which is already done now. So this is, for example, the filters that we are using. You can see here in this color in the back, which is the Euclid from the visible. The colors in the bottom are from LSST. And I am using images from the legacy survey, from the GDR and the C, to simulate what is going to be LSST. And the high resolution, I'm using images from the filter 814W. So it's more or less to try to simulate what is going to be both of them. And well, I'm using right now images from decals from the bottom, from the dark energy camera legacy survey. So, okay. So first, what we want to do, since we want to try and search to see lenses, but see if it's better to use colors or high resolutions, or if combine both of them, it's better. We need to first search for galaxies, because we need to simulate lenses to try to train the CNN. So to simulate this and try to look for galaxies, we search for then luminous red galaxies as the lens. And for sources, we use galaxies from the Hubble Ultra Deep Field. So now I'm using, since we didn't have enough lens systems for the training, then we create the mock images, and we are using a pipeline from Stefan Schultz from 2021, where more or less they paint the arcs in the galaxies so that we can have a very realistic lenses in the images. So first we took as input, I'm going to show you a little bit how we do the mock images. So we have the lens images from HST in this case first. As the source, we use the Hubble Ultra Deep Field. And then we use a lens potential that is modeled with we model the lens. We put the sources randomly positioned in the source plane, and we choose an Einstein radius that goes from 0.5 to 2.5 arc seconds. Then our lens into the image plane using a software. As you can see, this is lens then this is a lens source. We also then are convolved into the PSF. So in this case, we convolve it with a PSF of HST. Here's the image. And finally, we have our lens system. So we basically painted the arcs to obtain then this lens system so that we can have more lens systems for the training. And finally, what we did was to save the parameters, and we recreated the same mocks for the low resolution images so that we can have the same images in the different colors, the same systems in the different colors, and also in HST or the high resolution image. So for the training sample, it was very difficult to try to find images, and I know that maybe 6,000 images is not enough, but we are still creating more mock images because we have a lot of galaxies. I'm still searching for more galaxies. HST, it doesn't have a very big of images. So we more or less have 6,000 HST and legacy system images. As you guys, here I'm showing you, it's not visible, but this is the G band, the R band, the C band of the legacy survey. This is just a composite image. This is not in the training. And this is the HST image. As you can see, there is a very quite difference in the resolution, especially in the pixels, from one image to the other. And you can see more clearly here in the high resolution images, the arcs, when you create the mock images. These are then the positive. We also did augmentation because 6,000 images, it was not enough. So we rotated the images and create new lens systems to have 4 times that number. And we also have negative examples. We search also for normal galaxies, spirals with bars, normal luminous red galaxies to try to train the network. So from here, then, we apply the CNN to these positive and negative examples. And here we're doing some different things. First, in the first part, we are using both of the images where we use the GDR-C as the input differently. And we have two neural networks, but this is like the first step because we want to try if both of them it's better or not, or if it does a different to use the HST. So here, for example, in the rock curve, where we have the true positive, where in the X we have the false positive rate and the true positive rate in the Y-axis, this is just a logarithmic image of this above. We can see that we need to try to get as close as possible to 1, because this means that it's we don't have many more too much false positives in our sample. And in this case, what we are observing over here is that the legacy survey, which is the blue line over here, it's acting better than the HST. So this means that for now, the color is more important than one color with a higher resolution. So now the steps, what I'm doing, and it's running right now, is combine both of them and then apply a neural network where the images from the low resolution are being, how do you say this? I forgot the name, but I am moving to the same pixels as the HST. I completely forgot the name, sorry. And then we are creating then the neural network for these 4 images. This is a working process. And later, the idea is to use also the both images, but have different neural networks from them, then having an output to see if this also makes a difference. So we still have like many tests to go. So yeah, more or less in a summary, we are still, it is very promising to observe the strongly lensed supernova. I hope that we can have with the upcoming service something that we can have better measurements of H0. With my work, we want to try to decrease also the false positive rate. We rely too much on human inspections, so that is why we want to like reduce the number of trying to humans to observe the images. And you can also observe here, I left a few papers that are already published about different search lenses using different techniques, but also from the same groups or also in cluster environments. And finally, if you want to know about our group, you can just use your phone and QR this, or Collier Smokes also with this QR. So thank you.
We have time for a lot of questions. ¿Preguntas?
Pues, levante la mano.
No.
La persona de atrás había levantado primero, por favor.
Thank you. Thanks for the nice talk. So I have a question regarding the practical application once Rubin starts. So you will get a stream of alerts, and you cannot receive the full stream because it's so large that only community brokers will get it, and they will have to filter it for you. Have you talked to any of the brokers?
Yes, we have several brokers in LaSire. We have also, we have different brokers with all of the strong lenses that we have. We have a list of strong lenses where a possible supernova may explode. So we are using that list with different brokers. So we are always monitoring if maybe some supernova may explode. So we are using that with LSST. We haven't yet talked about that, but yeah, we have like different brokers that they will tell us if one supernova explodes.
Thank you.
Por aquí adelante, entonces.
Después.
Okay. So I have two questions. The first one is, because I didn't get it, do you assume a cosmological model for the distances to get the relation to H naught in the...
Flat lambda CDM.
Yes. Okay. So there is this assumption. And the other one is, I find this like a very interesting cosmological tool, but you also see that for this plot you show, and also you show too yesterday, there were the estimation of H naught for 6 systems, I think, which were very different, but then you got mean value of 73, yes. But then the distributions are different. So which would be the systematics of this in this in this method?
The errors, you mean?
The systematics involved in this in each system to take into account. I mean, this is quite new as a cosmological probe, but I guess we have to think now on the systematics to be improved or to be taken into account to use this, first of all, to combine the information from different lenses into one single.
Yes, I mean,
and
in general, the errors come at least from the models, also from the measurements of the variability, the light curves. And I know at least that this work, it cannot reach lower than this value over here. So we're for now with the telescopes that we have. So we are not being able to reach the 1%, at least with the precision, but with the strongly lensed supernova, we are able to reach lower of this precision. So for now, I know that they are different light curves and they have different systematics and everything, but this work is already done. And I think it's included one more lens to this H0 measurement, but yeah, their TD Cosmo try to refine this number, but it is very difficult. So that's why we moved now to a strongly lensed supernova.
There's a question over here.
Una pregunta por aquí.
Yeah, hi, I have the microphone here to your right, up here. Hi.
Okay,
Yeah.
I see you.
It's okay. So your last slide went very fast on the combinations you're going to use for the filters. And I think you, you get to that. After that one, after.
This one?
Yeah, there. Okay.
Okay.
So you're here to do for you is still using the legacy survey, but I wonder how you would expect this to change once you use Euclid, because Euclid will give you better resolution, probably colors will change.
Yes, I mean, the idea, I'm here. Yes, here I'm using the legacy survey, which simulate LSST. So there are more or less the pixel size of all of the images, while for the high resolution, which is HST, we have 0.05 SAR second per pixel. In Euclid, it's 0.1. I have already seen images of Euclid because we had already the early release images, and we have compared some images with HST, and they look pretty much similar. We're doing some tests right now. but at least all of the models that have been done before are in accordance to what we cannot do with HST. So it shouldn't change much how the architecture varies when changing HST by Euclid, but we shall see then when we have more images of Euclid, and then maybe we can, because now we are testing on real images on Euclid and trying to refine that. So in the future, we will see how we will change this. Like maybe the architecture changed a little bit, but yeah, for now it's a little more or less concordance to what we have.
Thank you.
Gracias.
Bueno, thank you for the nice talk. I have a question regarding with the physical system that you are choosing.
sorry.
So you,
I cannot see you.
here,
Okay. Sorry.
I understand why you are not now focusing supernovae lens, especially you find a 1A system, which is not the case in the table that you show. It's half and half. Core collapses, or sometimes it's also difficult. I don't know how this compare with quasars. In order to really know the luminosity of the systems. My point is the number of supernova lens that you show is quite low. So how much do you expect to increase the number with new survey, and how this compare with other systems like quasar and I don't know which other?
Okay, yeah. The forecast for a strongly lensed supernova, at least the number that we have right now, is 10 supernova per year. So it's still like pretty low. But even though we observe 1 or 2, the precision is very low. I mean, we have a very good measurement of H0 with just 2 systems. So even though it's just 10 per year, we still can obtain a very good result. And regarding the quasar, well, lens supernova, I think it's, at least for the time delay, it's pretty much faster, but we need to have a very rapid, when one supernova or one alert say, okay, this is a supernova, we have to take an image and then do the lens modeling and then try to get to another telescope to observe it again. So it's pretty much going to be a little bit faster to obtain that, but we have to be very quickly. So we have like different projects there that are waiting to see if we can observe a lens, like a lens supernova.
Muy bien, una última pregunta por aquí.
Hi. In the last part on the models, yeah, this. You talked about resampling down the Hubble images,
No, we are
sampling.
upgrading the legacy survey to the Hubble images.
Okay, okay.
Yes.